9.4 QoS Models. 9.4.2 Selecting an appropriate QoS policy model. How can a QoS be implemented in a network? There are three models for implementing QoS. The best effort model, integrated services, and the differentiated services. This table summarizes the three models. QoS is implemented in networks using either int_serve or diff_serve. While int_serve provides the highest guarantee of QoS, it's very source-intensive and therefore not easily scalable. In contrast, the diff_serve is less resource-intensive and more scalable. The two models are sometimes co-deployed in the network QoS implementations. For the best effort model, this is not really an implementation as QoS is not explicitly configured. Use this when QoS is not required. The integrated service, the int_serve, provides a very high QoS to IP packets with guaranteed delivery. It defines a signaling process for applications to signal to the network that they require special QoS for a period and the bandwidth should be reserved. The int_serve can severely limit the scalability of the network. The differentiated service, the diff_serve, it provides high scalability and flexibility in implementing QoS. Network devices recognize traffic classes and provide different levels of QoS to different traffic classes. The basic design of the Internet is the best effort packet delivery and provides no guarantees. This approach is still predominant on the Internet today and remains appropriate for many purposes. The best effort model treats all network packets in the same way. So an emergency voice message is treated the same way that a digital photograph attached to an email is treated. Without QoS, the network cannot tell the difference between packet and as a result, cannot treat packets preferentially. The best effort model is similar in concept to sending a letter using standard postal mail. Your letter is treated exactly the same as other letter. With the best effort model, the letter may never arrive, and unless you have a separate notification arrangement with the letter recipient, you will never know that the letter did not arrive. This table lists the benefit and the drawback of the best effort model. The benefits are the model is most scalable. Scalability is only limited by available bandwidth, in which case all traffic is equally affected. No special QoS mechanisms are required. It's the easiest and the quickest model to deploy. But there are drawbacks, such as there are no guarantees of delivery. Packets will arrive whenever they can and in an order possible if they arrive at all. No packets have the preferential treatment. Critical data is treated as the same cordial email is treated. The int_serve architecture model was developed in 1994 to meet the needs of real-time applications such as remote video, multimedia conferencing, data visualization applications, and virtual reality. int_serve is a multiple service model that can accommodate many QoS requirements. It delivers the end-to-end QoS that real-time applications require. int_serve explicitly manages network resources to provide a QoS to individual flows or streams, sometimes called microflows. It uses resources reservation and dimension control mechanisms as building blocks to establish and maintain QoS. This is similar to the concept known as the hard QoS, where hard QoS guarantee traffic characteristics such as bandwidth, delay, and packet loss rates. From end to end, hard QoS ensure both predictable and guaranteed service levels for mission-critical applications. InServe uses a connection-oriented approach inherited from telephony network design. Each individual communication must explicitly specify its traffic decipher and requested resources to the network. The edge router performs admission control to ensure that available resources are sufficient in the network. The InServe standard assumes that routers along a path set the maintain and state for each individual communication. In the InServe model, the application requests a specific kind of service from the network before sending the data. The application informs the network of the traffic profile and requests a particular kind of service that can encompass its bandwidth and the delay requirements. InServe uses resource reservation protocol to signal the QoS needs of an application's traffic along devices in the end-to-end path through the network. If network devices along the path can reserve the necessary bandwidth, the originating application can begin transmitting. If the requested reservation fails along the path, the originating application does not send any data. The edge router performs admission control based on information from the application and the available network resources. The network commits to meeting the QoS requirements of the application as long as the traffic remains with the profile specification. The network fulfills its commitment by maintaining the per flow state and then performing packet classification, policing, and intelligent queuing based on that state. The table lists the benefits and the drawbacks of the InServe model. The benefits are explicit end-to-end resource admission control, per request policy admission control, and the signaling of dynamic port numbers. The drawbacks include resource-intensive due to the stateful architecture requirements for continuous signaling. The flow-based approach not scalable to large implementations such as the Internet. The differentiated service, DiffServe, QoS model specifies a simple and scalable mechanism for classifying and managing network traffic. For example, DiffServe can provide a low-latency guaranteed service to critical network traffic, such as voice or video, while providing simple best-effort traffic guarantees to non-critical services, such as web traffic or file transfer. The DiffServe design overcomes the limitation of both the best effort and the InServe models. The DiffServe model is described in the RFCs 2474, 2597, 2598, 3246, 4594. DiffServe can provide an almost guaranteed QoS while still being cost-effective and scalable. The DiffServe model is similar in concept to sending a package using a delivery service. You request a level of service when you send a package. Throughout the package network, the level of service you paid for is recognized, and your package is given either preferential or normal service, depending on what you requested. DiffServe is not end-to-end QoS strategy because it cannot enforce end-to-end guarantees. However, DiffServe QoS is a more scalable approach to implementing QoS. Unlike InServe and hard QoS, in which the end hosts signal their QoS needs to the network, DiffServe does not use signaling. Instead, DiffServe uses a soft QoS approach. It works on a provisioned QoS model, where network elements are set up to service multiple classes of traffic, each with varying QoS requirements. Now let's talk about a simple div-serve example. A host forwards traffic to a router. The router classifies the flow into aggregates and provides the appropriate QoS policy for the classes. Div-serves enforce and apply QoS mechanisms on a hop-by-hop basis, uniformly applying global meaning to each traffic class to provide both flexibility and scalability. For example, div-serve could be configured to group all TCP flows as a single class and allocate bandwidth for that class, rather than for the individual flows as intserve would do. In addition to classifying traffic, div-serve minimizes the signaling and the state maintenance requirements on each network node. Specifically, div-serve divides the network traffic into classes based on business requirement. Each of the classes can then be assigned a different level of service. As the packets traverse a network, each of the network devices identifies the packet class and services the packet according to the class. It's possible to choose many levels of services with div-serve. For example, voice traffic from IP phones is usually given preferential treatment over all other application traffic. Email is generally given best effort service, and non-business traffic can either be given very poor service or blocked entirely. The table here lists the benefits and the drawbacks of div-serve model. For the benefits, it's high scalable, provides many different levels of quality, but there are drawbacks, and these drawbacks include no absolute guarantee of service quality, requires a set of complex mechanisms to work in convert throughout the network,